My name is Cameron Bernardo, and today we will be learning about Babylonian mathematics. The Babylonian civilization dates back to 4000 BCE with the Sumerian civilization in Mesopotamia. Sumer was developed between the years of 4500 and 4000 BCE by people who did not speak the Sumerian language, and they were called Euboeans. The Euboeans were the first civilization in the region until the Sumerians came from Anatolia in 3300 BC. The Sumerians did not have writing for numbers, and because of their scarce resources, they used clay and a stylus to write on, sort of like today's pen and paper. One of the most powerful leaders was Sargon the Great, who ruled from 2276 BC until 2221 BC. While Sargon the Great ruled, the land was shammed into an empire called the Dynasty of Akkad, and in result, the Akkadian dialect replaced Sumerian. Around this time, irrigation canals were built to connect to the Tigris and the Euphrates River, and the canals were essential for civilizations to thrive. In 2218 BCE, the Gutians conquered Akkadian, and that resulted in the third dynasty of Ur. Then the Elamites came and demolished Ur in 2000 BC. No one gained complete control until Hammurabi of Babylon, who ruled from about 1792 until 1750 BCE. There were two types of writing tablets found, and they were the table text and the problem text. The table texts were the multiplication tables, the weights and measure tables, and the reciprocal tables. The second class tables contained the solutions or method of solutions to algebraic or geometrical problems. Some problems contained up to 200 problems and gradually became more difficult than the last. Babylon fell to Cyrus of Persia in 538 BC, but the city was spared. Another era of Babylonian mathematical history happened in about 300 BCE when Seleucid. That 300-year period was equipped with a lot of astronomical records, which are usually compared to Ptolemy's Almagest. The Babylonian number system was positional but sexagesimal, which means that it had a base of 60. They didn't use zeros, and some fractions weren't used, but they could square root, they could solve quadratic equations, they could solve cubic equations, and linear systems. They also worked with Pythagorean triples. They solved cubic equations with the help of tables and studied circular measurement. These two symbols were used by the Babylonians to represent their numbers. This would represent a 10, and this symbol would represent a 1. The 1 could be used up to 9 times, and the 10 could be used up to 5 times because it couldn't go past 60 because the base is 60. This symbol, when put together, was used to represent a subtraction sign. Okay, I've given you the information. Now we're going to do some problems. Okay, this is the first problem. I'll give you about 5 seconds, or you can just pause the video, and when we come back, I'll tell you what the answer is, and I'll explain it also. Okay, we're back. The answer was 35. Alright, since this represents a 10, do it this way. Since this represents a 10, since this represents a 10 and this is a 10, this would add up to be 30. And over here, remember, you have your ones, and that's 1, 2, 3, 4, 5. So your answer would be 35. Did you get it right? Alright, here is the second example. Again, I will give you about 5 seconds, or you can pause the video, and I will have the answer when we come back. The answer for the last example was 19. Where's my Anyway, this represents a 10, and this represents a 10. However, this is the minus sign I was talking about earlier. Let's see, did you catch it? Anyway, this is a 1. So 10 plus 10 minus 1 equals 19. Alright, third example. Oh, it's a big one. Alright, I'm going to give you 5 seconds, and I'll be explaining it when we return. Alright, this problem actually shows that the Babylonians understood place value. And for you, I have sectioned off the different sections. So this is section 1, which is just this one. This is section 2. This is section 3. And this is your 4th section. Okay. Now, when solving a number this large, you have to understand that if you start at the right, your exponent should, well, your exponent over the 60 should go in ascending order. So it'll be 60 to the 0, 60 to the 1st, 60 to the 2nd, and 60 to the 3rd power. Okay, so now the value that was in your first section, which is this one, when you add it up, it will go with the 60 to the 3rd power. And your sum in the second section, which is right here, will add up to be 28. 10, 20, 21, 22, 23, 4, 5, 6, 7, 28. Will go with your 60th to the 2nd power. And all of the numbers in the 3rd section will add up to go with your 60 to the 1st power. And all of your numbers in the last section, can you see it? Yeah. All the numbers in your last section will go with the 60th to the 0 power. Alright, now we will use PEMDAS. Can I say that? I use PEMDAS, I say PEMDAS. Now we're going to use PEMDAS, which is please excuse my dear Aunt Sally, to solve this problem. So you solve what's in the parentheses first individually, and then at the end, where am I? At the end, you will put in your addition signs, and you will end up with the answer of 319,940, and that will be your answer. Okay, now we'll be adding modern numbers with a base 60 to get the answer, basically. Oh, I forgot to tell you, this is your first example. 325, 4. 5 seconds. Okay, you will solve this problem just like the last problem, except for you don't have to count the Babylonian numbers. They give you the numbers already. Okay, so where's my pointer? I'm going to have 3, which is 3 times your 60 squared, plus your 25, which is there, times your 60 to the 1st power, plus 4 times your 60 to the 0 power. You add those up individually, get 10,800 plus 1,500 plus 4. And you will get the answer, well, you should have the answer of 12,304. Next, we will be solving the square root of 2. Okay, these are the steps to finding the square root of 2. I've numbered them on the side. Okay, first we're going to take a equals a1 as an initial approximation. Alright, if a1 is less than the square root of 2, then we're going to put 2 over a1 is greater than the square root of 2. Then we will solve the equation a2 equals a1 plus 2 over a1 all over 2. And then we will repeat until we get a very, very close approximation. Okay, I've done the problem for you. And this is in the format, well, it's going to go by the rules that I just said. So for a1, I picked 1 because it's less than the square root of 2. So for a2, we're going to substitute 1 for, you know, the previous problem that I gave you, which is the A1, well, no. Yeah, A1 plus 2 over A1 all over 2. So we substituted the 1 right here and the 1 right here. And so after solving this, we will have 3.2, well, 3 over 2, which is equivalent to 1.5. We will repeat, and we're going to have 3 over 2 plus 2 all over 3 over 2 all over 2. And that's going to be 1.41666 repeating, which is 17 over 12. Then we will repeat one more time. And we'll have 17 over 12 plus 2 all over 17 over 12 all over 2. And that's going to be 577 over 408. And that is approximately the square root of 2. And it was actually 4 decimal places off, which is very good for the Babylonians. The Babylonian method for solving quadratics was based on completing the square. In their equation, they only used positive numbers, which gave them positive solutions. And negative solutions did not come about until the 16th century CE. Okay, so they would, the way they solved their quadratic equations is they would take a, quadratic equation like this, and they would actually follow a template for quadratics which had solutions of a specific problem of the correct mathematical type, but they were all written rhetorically, so they didn't really have a specific method to write quadratic equations. Okay, now solving the cubic equations is, well, I think it's very similar to how we solve cubic equations. We start off with the cubic equation, which is 2 to the third, let's see, 3 to 1. And we actually take out an x where it's needed, and then we end up with a quadratic equation. And of course they know how to solve that by the templates. Linear systems were solved by reducing a problem of 2 variables to 1 in an elimination process, which is very similar to Gaussian elimination. Okay, now we're going to do an example. This is my system of linear equations, which is 2/3 x minus 1/2 y equals 500, and x plus y equals 1800. Now I want to make my x1 equal my y1 such that x1 plus y1 equals 2x, which comes from this equation, equals 1800. And we're going to divide by the 2 to get x1, and your x1 will actually equal 900. Now I want x to equal x1 plus d and y to equal y1 minus d. Okay, now with this equation, this first equation comes from the top, what we started with, and I want to substitute my x to equal the x1 plus d, like I said before. So now you will have 2 over 3, and for x you want to put 900, which is your x1, plus d, minus 1/2, and I want my x again to be, well, I want my y now to be 900 minus d equals 500. Now we will be distributing the 2 over 3 to the information in your parentheses, and the negative 1 over 2 to the stuff in the parentheses, and we will have 1800 over 3 plus 2/3 2 over 3d minus 900 over 2 plus 1/2 d, all equaling 500. Now we're going to clean it up, and we'll have 600 plus 2 over 3d minus 450 plus 1 over 2d equal 500. When you subtract 450 from 600, you will have 150 plus 2/3, well, 2 over 3d plus 1 over 2d equaling 500. Now we're gonna, well, you subtract the 150 from 500 to get 350, And now you're gonna take out the 2 over 3 plus 1 over 2 since they have a d in common. You're gonna add those two together to get 7 over 6d equaling 350. Your d should then equal 300. What am I doing? Okay, now you're gonna go back to the x1 plus d equals x and your y1 minus d equals y. And since your x1 was 900 and your d is 300, your x is going to be 1200. Now I'm going to go back to my original problem here and plug in my x to get my y. And then I will have 1200 plus y equaling 1800. And when you subtract 1200 from 1800, your y will equal 600. So now you have your x and your y. And you can check that by basically plugging the 1200, which is your x, plus your y, which is 600, into your one of your original equations. You can pick any of those two, but I would recommend this one since it's easier, and it should equal your 1800. Just like the ancient Chinese, the Babylonians were aware of the Pythagorean theorem, and the Plimpton 322 tablet demonstrates their understanding of Pythagorean triples. Pythagorean triples are basically any set of positive integer a, b, and c that fits the rule of the Pythagorean theorem, which is a squared plus b squared equals c squared. Okay, for examples, I have here the smallest Pythagorean triple, which is 3, 4, and 5. You have your Pythagorean theorem here, and now you're going to plug in your 3, your 4, and your 5. 3 squared plus 4 squared equals 5 squared. 3 squared is 9, 4 squared is 16. You add it up, get 25, which is 5 squared. And the next Pythagorean triple is 11, 60, and 61. You have 11 squared plus 60 squared equals 61 squared. 11 squared is 121 plus 3,600 for 60 squared, equaling 3,721 for your 61 squared. And if you add that up, it will equal 3,721. So it is a Pythagorean triple. Babylonians generally used geometry for construction and land estimation, like areas and volumes and rectangular objects. The Babylonians usually used their algebra methods to solve for geometry. However, there's no indication that they had logical proofs for the correctness of their rule-based methods. Well, that's my time. Thank you for watching and listening, and I hope you enjoyed my lesson on Babylonian mathematics. Bye.